All right, so this is the final problem of the USACO Bronze December 2022 contest, and it is called reverse engineering. So the problem statement is here. LC has a program that takes as an input an array of n variables. N is less than 100. That'll be important. B0 to Bn minus 1, and each of these is set to 0 or 1. And then she returns the result of applying a sequence of if, else if, and else statements on the input. Each statement examines the value of at most one input variable and returns either 0 or 1, like something like this. And so if the input is 10, then B0 is 1 and B1 is 0. So this will go to the else if because the if will return false, and B0 is 0. So this will also return false, so it'll skip both of these and it'll return 1 at the end. So yeah, then the output would be 1. And Elsie has told Bessie the correct output for m different inputs. M is also less than 100. And now Bessie is trying to reverse engineer Elsie's program. But Elsie might have lied, and it might be the case that no program is consistent with what Elsie said. So we need to determine whether Elsie is lying. So the important thing to note about this problem is that n and m are both pretty small. Also, there's t test cases where t is at most 10. I guess a good rule of thumb is that a computer can operate about 10 to the 8th operations in a second. And this means that we can do something that's like 10 squared, 10 times 10 squared cubed. This would equal 10 to the 7th, which would be within our limits. So, for example, we could have a solution that's O of t times n squared, or O of t times n squared times m, or anything where the sum of the exponents of n and m adds to 3. As it turns out, our solution will have this time complexity here, and we'll basically see how that works in a bit. But this is going to be the general idea for this problem. The fact that we're a little more lenient with what we can do, because n and m are so small. Okay, so let's go back to the problem and see what it is. So with the sample input, I think these are all fairly self-explanatory, so I won't go into them too much. The idea is that each test case, we first are given t, and then for each of the t test cases, we're given, I think it's n followed by m. So this is n and this is m. And then we're given the strings. So in this example, there is no valid program, for example, because 0, 0 leads to 0, 0, 1 leads to 1, means that the second bit must be part of one of these. Well, both of these bits must be part of this if and else configuration for it to be possible. However, you can see that it's totally inconsistent with either of them. So how do we actually check this as an algorithm? And I'm going to say that this algorithm is kind of brute force, or greedy, whatever you want to call it. But the sketch here is going to be just like iterate through bits and see if they can be used in an if or else if split. And I'm going to use this word split a lot. So what this means is, for example, if we had an input where we have a lot of, let's like ignore what's actually here for a sec. But let's say that we have some bit that I'm going to call j, and maybe it equals 0 for a bunch of inputs and 1 for the rest. So this can be used in an if statement. In the very first if statement, if like all of these correspond to the same value. So let's say all the zeros correspond to zeros, or all the zeros correspond to ones in the output. Then we could do something like if bj equals 0, return 0, or return 1, or whatever it might be. We could do something similar if, for example, all the bj's are 1. So maybe these are all zeros, and then it would be something like if bj equals 1, return 0. So that's how it would work for the very first if statement. And I also claim that these splits are things that you can see for these nested else and else if statements. So what that means is that for an else if statement, like within nested statements, we can basically ignore the strings that have been split away, or that have been already like returned. Which means it's possible that if something doesn't induce a split at the very beginning, maybe other splits will like help it be able to produce a split later on. So our solution will be to iterate through all the bits and see if they can be used in any split. And let me erase this here so I have more space. If so, do the split. And this is what I'm going to call the greedy part of the algorithm. Because initially you might think like, well, does the ordering of these splits matters? Like if in one like iteration of this, where we've thrown away a bunch of strings that have been returned, how do we choose between taking like one bit that like would chop off like half our data and another bit that would also do the same? And I also claim that it doesn't matter which one you do first. So let's say that you have a bunch of, say this is bi, or I'm going to use bj, and these correspond to zeros and like maybe some other stuff. And this is a valid split. And on the same data, you have something like this. So if these are our bits and this is our output, and let's say this is bk, then note that you could use either bj equals 0 or bk equals 0 to do a split right now, because all the bk equals zeros correspond to zeros, and all the bj's equals zeros also correspond. Oh, actually, you could not do split with this. May do something like this. Yeah. So all the bk's, sorry, was fine originally. All the bk equals zeros correspond to zeros. So this is a great split. So it doesn't matter which one you do first, because if you end up nesting these two, then we can nest them in any order. So let's say we have like else if bj equals 0, and later on we have else if bk equals 0. Both of these splits will be able to execute the return statements like in any order. And since both of them are valid, if we like swap these two, it won't affect the actual execution of the program. We're only dealing in these return statements with splits that we haven't seen previously. So yeah, that might be a little confusing, but the essential idea is that we can do this very greedily. Okay, so now going back to this algorithm, we will take these, iterate through the bits, and see if they can be used in an if-else split, and if so, execute the split. If not, then we're done making splits. So what does it mean once we're done making splits? Well, hopefully we've reached the else return statement in our code. And in this case, once done, we just need to check that everything in the input we just need to check that there's only one type of output left in the set of strings that we haven't already returned outputs for. So here we check if there's only one output left, because then we could just return it. So yeah, so intuitively this might make a lot of sense, but I think coding it up is better for seeing how this actually works in practice, because I think the implementation is probably the trickiest part of this problem. So yeah, let's code this up. And here. Okay, so start by including bits. And then we're going to start with our auxiliary variables. So we'll store our list of strings. These are LC strings. And then our list of outputs. We're going to keep track of this array used, which just means we keep track of which bits we've already used to make a split, because we can't actually use them again. And then we will have n, m, and t as our variables too. So now let's go into our function. So we have in main, and the stuff here. Here we just read in a string followed by the output. And then for, I'm going to use j to refer to bits and I to refer to strings in the rest of the code. So we initialize everything and use j to be false, because none of our bits are used initially. Okay, and now we will have our main loop where we keep trying to execute splits, and then seeing if they work, and if so, we make the split. So I'm going to actually just use an infinite loop for this, as it's going to be the simplest, because our stopping condition is like once we're not able to make a split. And I'll put an if statement here to check if that happens. So while true, we will have a variable called split found, initially false, and we'll set this to true once we found a split. So first we try splitting by each bit. What that means is that we iterate. So and then now we'll try each of these splits. So you could just write the splitting code here. It's going to be like a bit complicated. So I'm going to just make a function that we call every time we want to test a split. So let's define this function split, which will take in a position, like a character, which will be like what you want to compare to, and an output. So there are 4 different types of splits. This would be bj equals 0, then return 0. This is bj equals 0, then return 1. This is bj equals 1, then return 0. And this is bj equals 1, then return 1. And if any of these is true, then split bound equals true. Great. So we will define this function later, but for now I'm just going to call it a Boolean split that takes in a j, something that we compare it to. And this will basically mean if bj equals comp, so we'll check if this statement produces a split. Okay, so now assuming that we've defined the split function, we can check if not split bound. Then we print lie. Exit early. But if and then we can check if all the outputs are the same. If this is ever true, then we know we're done. So we can just check this every loop. And for that, I will write another function too, called all equal. So if all the remaining strings are equal to 0 or 1, or sorry, all the remaining outputs are equal to 0 or 1, then we print OK, and we break. All right, so that's like the main idea of this code. It's to check splits. And if we ever can't find a split, return lie. And if all the outputs are ever the same, then we return OK. So now let's actually define these functions. So let's start with the easier of the two, which is checking all equal. So we need to, here we're passing in like an output. So I'm going to call this test out. And we basically need to check if all the outputs are test out. So iterate through all the strings. And to keep track of which strings we have already like split away, we can just set them to empty strings. It's, I think, the simplest way to do it. So we have this function here. And if the output, so if we have a string that's not been taken care of and its output is not equal to test out, then we return false. Otherwise, if we get through everything, we return true. All right, now let's define split. So the idea here is that we will see if there is a valid split. And then if so, we will set all the strings for bj equals comp to empty strings to signify that we've taken care of them. So first, if use j, false, we're not going to reuse any position that we've already used before. And now we have our iteration. So we were only going to check non-empty strings that have not been taken care of yet. And strings where the bit j is equal to comp, and I is not equal to out. This means that we could not use this actual split. Then we return false. Because remember, out is our desired output for here at this. So if there's a string that satisfies this if condition, but doesn't return our desired output, then it breaks it. So that means we need to return false. Otherwise, we actually do the split because we've gotten through every string and everything works. So to do the split, first we'll make sure to set useJ to true to signify that we have used this bit. And now we need to set strings where bj equals comp to empty strings to indicate that they've been taken care of. So for I equals 0, if string is not empty and ij comp, then we set strings I to an empty string. And finally, once we've gone here, we know that we've produced a split, so we return true. So yeah, that is the entire code. The main ideas here are we have these functions that will make our code a lot simpler, which produce splits and then check if they're possible at the same time, as well as check if every string that's remaining has the same output. And then that makes our actual program code a lot simpler, which and easier to read, which is we tried splitting by each bit. If we find a split, then we're good, and we do that, and we do another loop. If we ever don't find a split, that means we failed, so we output lie. And in every iteration, we check if all the outputs are the same, because that means we don't even need a split on the next iteration, and we just can print OK. So yeah, that's the entire code. And then finally, we'll end with analysis of the complexity. So memory is pretty simple. We just have these arrays of size 100. So memory here is, I guess, O of n plus m. Or, oh, sorry. Each of these strings can be the size of the string, which is O of n. So this is O of n times m memory, which is 100 squared. So 10 to the fourth, which is fine. And then with our time complexity, we are iterating through m, all of the bits in the string once here. And that's what each of our split checks does. And we iterate through n here, all of our strings once, so that would be m times n. And then this loop itself can iterate at most n times, because we try splitting by each bit. And if a bit succeeds as being a split, we'll never try it again. So this is O of n squared n. And we also do this t number of times. So it's in total O of t times n squared m. And that's our solution.